Okay, we're talking about slant asymptotes now. We just got finished talking about horizontal asymptotes here with these two rules. And we're looking at the degrees of the numerator and the denominator. So when the degree is the same, the horizontal asymptote is a ratio of the leading coefficients. When the denominator's degree is greater, we always have y equals 0 as a horizontal asymptote. So where do slant asymptotes come in? For example, where do we get, something like this? Because you get some graphs that look like this, that clearly have something weird going on here, and here would be maybe a vertical asymptote, and here is a slant asymptote, or we also called it an oblique asymptote. Oblique. Okay, that means slanted. Okay? So this happens when, so this would be kind of hint number 3 for when you have a slant asymptote, is when the degree of the numerator in the rational function is greater than the degree of the polynomial in the denominator. And I won't get in this lesson. I will not get into what is the equation, although it's not that hard. But it requires long division, which no one likes. Who likes long division here? Polynomial long division? Anyone? No, did not see a single hand. Exactly what I thought. We don't need to do that. So if we're looking at this right here, y equals x squared minus 3x all over x. Okay, that's an example where we have the degree right here, and the numerator is greater. So let's graph it. Okay, so here we're graphing it. Oh, maybe this isn't a great example. Maybe we have to zoom out. Okay. What does this look like to you? It looks like a line, doesn't it? Yes. Now, I just randomly threw this example up here. Should it look like a line, or should it look like something like this right here? What do you say? Why? Because what? Ah, okay. Thank you. Because you can. Oh, x minus 3. Look at this. Check it out. Check it out. X's divide out, so it just actually is going to end up looking like this. Now, it just so happens that this would be the equation of the slant asymptote if we weren't able to divide anything out. Okay, but this is actually not the example that I really wanted for you. But this would where the horizontal asymptote would be. So, how can we adjust this one so that we don't have anything divide out like this? What could we do? So that we still have an x in the denominator. I'm going to change something. What are we going to change? Any ideas? Okay, so x squared minus 3. Okay, let's see. If we factor this, can we factor this? Well, the answer is actually yes. Okay, no, just don't get excited yet. Okay, listen, I'm not saying you're wrong, okay? I'm not saying you are wrong at all, but we can factor this. Now, here's the thing. Up until this point, you guys have all been good little boys and girls and taught to notice that, hey, this is not a difference of squares, Mr. Maxwell, because this is a perfect square, but 3 is not a perfect square. It's not a perfect square. Well, actually, now that you're grown-ups, now that you're entering, the calculus world, this actually is a perfect square. Why not? What is its square root? Okay, maybe it's not a perfect square. Let me back up. It's not a perfect square, but can you take the square root of 3? No, not 1.73. No, not decimals. How else could you write the square root of 3? Hello? Okay, so when you say that we can't factor this, the actual reality is that we can factor it as a difference of squares. But can we divide out a common factor No, the answer is no. So, okay, let us go to the calculator, put this in here. Okay, let's try it. X squared minus 3. Let's just see if Amy was right, right? Let's just see. There is a remote possibility. I'm going to use my brackets here. Divided by x. Okay? Now let's see. Oh, I'm going to go zoom 6, so we're not zoomed out too much. Wow! Check it. That's actually pretty groovy. That's pretty groovy. Looks like it's doing kind of like this thing. That's what it looks like. That's what it looks like. Do you like that? That's the only dance move I have. Sorry. No, I'm not going to keep doing it. No. Because here's the reason why I'm not going to keep doing that. Because you are laughing and I am not. So you're not laughing with me. You're laughing at me. So therefore, I am not going to keep doing it. Okay? Yeah, well, my wife thinks I'm groovy. Because she brought me a coffee that you won't let me drink.
You're not letting me drink it.
Okay, we should not be talking about my wife's feelings about me right now, okay? Just so you know. You guys, it wasn't me. It was all you. That's all I hear. That's all I hear. No one's listening to you. Okay. Okay, fine. Hey, but listen. Check this out, though. Look at it. You see? Now, you did this? Okay, good job. Very groovy. But now look, there's a slant asymptote here. Okay? A slant asymptote. All right? Now, I'm not going to get into what the equation of this oblique slant asymptote is, but just suffice it to say that there is an oblique asymptote. So, asymptote. So when the degree of the numerator is greater than the degree of the denominator, you have a slant asymptote. Yes, I accidentally said asymptote. Thank you for being so mature. That's what I'm going to call my kids next time they're misbehaving. Hey, little asymptotes, get over here. All right. So once again, if the degree is greater, you have a slant asymptote. Now, if you want to know what the slant asymptote is, the equation of the asymptote, first of all, I don't require you to know the equation of the slant or oblique asymptote. If you want to find out, as I mentioned earlier, what you do is you'd have to do the long division and actually find out what the quotient is, which we can do. I probably will do at the end of this session here. But you do the long division, and whatever the quotient is, whatever the answer is up on top there, that is the equation of the slant asymptote. There's going to be a remainder, right? There's going to be a remainder here when you divide out. But whatever it is up on top there, that is the equation of what the slant asymptote would be. So it's not that hard, but it's just, I just don't think I'm going to need you to do that right now. Okay? So, anyways, I guess the only other thing that I was going to mention, if you have something like this, and you say, well, this is not a clear-cut rational function. Well, it is, but it's all separated up, right? So what do? Do you look at the degree of this one and the degree of this one, and then that's it? No. You got to get everything into one term. So if you combine everything into one single rational term, then you compare the degrees. So right now, right now, you can't use those rules and just look at this part. Okay, so I'll just flesh this out. Okay, to get this into one single term, we're not going to want to multiply. Did you say multiply everything? Yeah, close. Okay, close. What you want to get is you want to get a common denominator. And so that means that everything has to have x plus 2 underneath it. And when you do that, in order that you don't change the terms, you have to multiply the top as well by that. Okay? So, some of you are already thinking ahead here, and you can probably already tell what kind of asymptote there's going to be. Okay? Does anyone know at this point? Sorry? A what? Just say it a little louder. An oblique. Okay, oblique. Is that what you said? A slant asymptote. Okay, do you want to tell the people why? You're right. The numerator here is going to have an x squared in it. Where is that from? Right here. The denominator will only have an x in it. So yes, we're going to have an oblique asymptote. Let's finish this real quick. So if we gather all the like terms, this is what we end up getting. And yes, you see that we have a squared and then to the power of 1. So this is going to be an oblique asymptote. So can we can factor this. Can we reduce this, or is there going to be a vertical asymptote at x equals -2? That's my question. Can we factor this? Yeah, we can actually. It's going to be x minus what? What are the numbers that go there? X minus 4, good. Plus 1, right? Because those two multiply to this and add up to this. So are we going to be able to divide any common factors here? No. So this is a vertical asymptote. All right, we have zeros at +4 and -1. We have a vertical asymptote here. You could quickly find out what your y-intercept is and so on and so on. And we have a slant asymptote. All right, so when you do long division, it's not worth hating. But you have to add the 0 terms there that you're missing. So it has to be a decreasing order of x always. Yeah, you guys know this already. Divided by x. I don't know. Yeah, this is polynomial long division. Fill in the spots for all the things that aren't mentioned, so there's the x term here. Okay, so x times what gives you x squared? X. X times x. You multiply those out, that's x squared. Wonderful. Do your subtraction. This minus this is 0. That should happen. Bring down this. 0. X times what gives you 0x? Well, plus 0. Okay, fine. 0x. Do your subtraction. 0. Bring down the -3. X times what gives you -3? Nothing. 0. X times 0 is 0. Yeah, so x would be your only, because you're down here. Keep going. So x plus 0 plus 0. So x is your, and remainder 3, -3. Because look at x squared minus 3. You could do x divided by x. That gives you x. Right? And what's left over? This minus 3. X is the equation of the oblique asymptote. Y equals x. Should be. So this is the graph of it right here. And if we also graph y equals x, that should be the equation of your asymptote. See that? So that's how you find the equation of your asymptote. You could use synthetic division as well. So this, no, yes, it's 1x, but remember it's the a value that you have to put here, so it's actually 0. So watch this. 1 drops down. 0, add 0. 0, add -3. So what the answer is just x to the power of 1. It's 1 less than this. So that's your quotient. Quotient.